All right, so our last topic was obviously our introduction to calculus, differentiation. And so this topic is called Extending Calculus. We're extending a little bit on what we've learnt. And for starters, a lot of that is going to be to do with E. Okay, so this first exercise is a bit of a discovery kind of opportunity, not the kind of stuff you'd probably see on a test, but to kind of explore where this kind of stuff came from. So the first example here, it says, in basic exponential form is any number raised to the power of x. So that's what exponential form means, something to the power of x. And the graph that is there is the graph of y equals 2 to the power of x. So we want to be able to differentiate that. Okay, how on earth do you differentiate when there is a power of x? Okay, we learnt last topic, you know, normal stuff, like if it's x squared, you bring the power down to the front, leave the x and subtract 1 from the power. That's not going to work if the x is in the power, right? So we need a new strategy here. So the first thing we're going to do, it says to differentiate y equals 2 to the power of x from first principles. Do you remember doing first principles?
Yes.
Oh, well, some yes, some no. Okay. So, yes. So the first thing we need to do is we need to know what f of x plus h is, because that's a part of our formula. So everywhere where there is an x, you replace it with an x plus h. So it's 2 to the power of x plus h. Then the first principles formula is f dash equals, so the dash meaning derivative of the function equals limit as h approaches 0 of f of x plus h minus f of x all over h. So I can substitute into that formula. Remember that the limit part has to stay there until I'm ready to substitute it in. So f of x plus h was the first thing I worked out. It is the 2 to the power of x plus h minus f of x is the original function, which is 2 to the power of x. That all needs to be divided by h. Now normally, in the ones we're doing in last topic, we would hope to be able to cancel out a factor of h from that. Not quite so easy to do when the h is in the power, but there is some little rearranging that we can do. No, unfortunately. What I can do is that first 2 to the power of x plus h, I can use my index laws and I can split that up like this. So I can say limit as h approaches 0. Remember when you multiply things with the same bases, you add their powers? I'm going to reverse that rule. I've got some powers added, so I could change that to be 2 to the power of x times by 2 to the power of h. Okay? Minus 2 to the power of x. Now, it still doesn't mean that I can cancel out a factor of h, but it does mean on my numerator, there is a 2 to the power of x that is common in both of those terms, and I could factorize it out. So I'm going to do that on my next line. Limit as h approaches 0, factorize the 2 to the power of x out of the top, which leaves 2 to the power of h minus 1, because the 2 to the power of x has come out the front, all over h. Okay, now unfortunately that 2 to the power of h minus 1 all over h, we actually cannot manipulate that algebraically to solve it. But what we can do is we can take the 2 to the power of x out the front of that limit. Because it has no h in it, there's nothing that I can substitute into that 2 to the power of x there. So I'm taking it to the side and I'm going to put the rest of it at the end. Okay, so that means what I've discovered, my derivative is 2 to the power of x times by, okay, and it's the limit as 2 to the power of h minus 1 all over h. That would just be equal to some number which we're going to call m. Okay, and we probably should write in there where m is equal to limit as h approaches 0 of 2 to the power of h minus 1 over h. And you can write a little note there for you when you're looking at this later to say that this cannot be found algebraically. Okay, so we can't actually do it by subbing something into that limit there. But what we can do is have a look at our equation if I substitute in when x is equal to 0. So hopefully you've got a bit more room here than I do. When x is equal to 0, in that derivative, f dash 0, this is my original equation, which was 2 to the power of x, right? My derivative is 2 to the power of x, which is 2 to the power of 0, times by this number m. What is 2 to the power of 0? Just 1. So whatever my gradient is, it is just equal to that constant. It has nothing to do with that 2 to the power of x. It is equal to whatever that constant is. Now the m is actually equal to the gradient of the tangent at x equals 0. So coming back to this graph here, that is how you would need to find it. That's where it comes from. That m is equal to the gradient of the tangent at x is equal to 1. So I'm going to write that for you down there too. So m is the gradient of the tangent at its y-intercept, which was the point 0, 1. All exponentials, unless we manipulate them too much, go through that point 0, 1. So m is always going to be equal to the gradient of the tangent when x is equal to 1, or at the point 0, 1. More specifically, it says on the next page, that's just meant to be, yours has an arrow there. What we have just seen there, it says, thus for all exponentials, the derivative of something to the power of x is equal to whatever the original exponential was, the a to the power of x, times by this value m, where m is the gradient of the y-intercept, or at the y-intercept. We want to find out how this is special when it comes to this letter E, which you've seen before. E is defined as the number where the gradient is exactly 1 at that y-intercept. Okay, so if you looked at that y is equal to 2 to the x graph, it's not a 45-degree angle. That tangent wouldn't be a perfect 45 or a gradient of 1. But this number E, which is 2.7182, blah, 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 that number means that that y-intercept has a gradient of 1. And that is really, really special because it means that the derivative of e to the power of x is just e to the power of x times by 1. But who cares about times by 1? Derivative of e to the x is e to the x. And that's why this number is a special one that we use a lot in math. Okay, so that's this box here. Okay, that's the key idea. You don't have to derive it every time. I said it was a bit of a discovery lesson. But what we are going to do is this exercise down here. It's exercise 11A. It's only 2 questions. I'll stop the video though.